Now we're going to talk about angular velocity and angular acceleration. Remember in chapter 3 we defined the displacement, then the velocity, and then the acceleration. We're going to do the same thing now with discussions of angular problems. So let's define the average angular velocity and the instantaneous angular velocity. This delta theta we introduced in the last section is called the angular displacement. And delta t is going to be our elapsed time. So just in the same way that we define the angular velocity vector, the average velocity vector as the delta r, the change in the position, aka the displacement over delta time, we're defining the angular velocity as an angular displacement divided by the elapsed time. So there are analogies through this entire chapter. Almost every single equation in this chapter has an analogy in chapter 3. So it's just a displacement divided by a time. So you might say, well, let's see here. Angular velocity, that must mean how fast it's rotating. And I say, yeah, that's what we mean. If the angle is changing a lot in a particular amount of time, then that average angular velocity is going to be high. It's moving a big distance in an angular way, then angular velocity will be high. What units is this measured in? Well, angles are measured in radians and times are measured in seconds, so the units are going to be radians per second for the angular velocity. The instantaneous velocity is, guess what? I think you guessed it already. The limit as delta t goes to 0 of the angular velocity to get the instantaneous velocity. So, given what we know about angular displacements, we know that delta theta is positive for counterclockwise rotations. We wrote that down a few slides ago. We know that the angular displacement is negative for clockwise rotations. Well, the angular velocity is the angular displacement divided by the change in the time. Well, the change in the time in the world that we live in is always going to be positive because you want your clocks to run forward and not backward. So delta t is always going to be a positive number. And so the sign, meaning positive or negative, of the angular average angular velocity, or in fact the instantaneous angular velocity, is going to be governed by the sign of the angular displacement. So the angular velocity is positive for counterclockwise rotations. Same thing as here. For a counterclockwise rotation, we have a positive angular displacement and we have a positive angular velocity, and it's negative for clockwise rotations. They have the same sign convention. All right, a drill bit turns at 1,200 revolutions per minute. This is one way to write an angular velocity, 1,200 revolutions per minute, or RPM. Express this angular speed. Angular speed is always going to be like regular speed that we use. It's going to be the absolute value of the angular velocity, or the magnitude of the angular velocity in radians per second. Well, so I want to express that in terms of radians per second. How am I going to do it? Well, first part's easy. I need to convert minutes to seconds. And I know that there are 60 seconds per minute. So there's one conversion factor, and that'll kill the minutes and allow me to have seconds in the denominator. But I've got this revolution here. How do I convert that to radians? Well, the answer is that I know how many radians there are in one revolution. There's 2 pi radians for one revolution. So 2 pi radians is one revolution. We talked about it before in terms of degrees. 2 pi radians is 360 degrees, but 2 pi radians is definitely one revolution, because that means you're going once around the circle. So that's how to do the conversions. Then the revolutions are going to cancel, and we end up with 1200 divided by 60. That's the same as 120 divided by 6, and that's just 20 times 2 pi. That'll be about 4. 2 times 20 is 40, times pi is about 3, so it'll be about 120 radians per second. So it looks like it's this answer right here. You plug the numbers in, but 2 times 20 is 40 times pi. Yeah, that looks like about right. So that's how to do that kind of calculation and do the conversion. So a gymnast on a high bar swings through 2 revolutions in 1.9 seconds. Find his average angular velocity. Well, let's find his angular displacement. He's moving, in this case, in a clockwise direction. And so his angular displacement is going to be negative. So his angular displacement will be negative 2 revolutions because he's going clockwise. And then we need to convert revolutions to radians, 2 pi radians per revolution. And this will give negative 4 pi radians. That's his angular displacement. His average angular velocity is the angular displacement divided by the change in time, the elapsed time. Plug the numbers in, and we get negative 6.61 radians per second. And we've got the right units here, radians per second, for the angular velocity. Define the average angular acceleration and the instantaneous angular acceleration. And you say, well, I'll bet I know what that is. I learned it in Chapter 3, and that is that an acceleration is going to be a change in velocity divided by a time. And you'd be absolutely right. That's exactly what happens here. The angular acceleration is denoted by the Greek letter alpha. So that's the Greek letter alpha. And there's a bar over it to denote that it's an average. And it is a change in a velocity divided by a change in time. And in this case, since we're talking about angular acceleration, we're talking about angular velocity. It'll be measured in what units? Well, angular velocity, what units is it measured in? Well, it's a displacement over a time, so it's radians divided by seconds. So this is radians per second in the numerator, and we're going to divide that by seconds in the denominator. That gives radians per second squared. So that's the units of average angular acceleration. So displacement, velocity, and acceleration in Chapter 3 were measured in meters, meters per second, and meters per second squared, respectively. Displacement, velocity, and acceleration in the angular sense in Chapter 8 are measured in radians, radians per second, and radians per second squared. So, and then just as you might have guessed, the instantaneous angular acceleration is measured in the same units, but it's the only difference between that and the average angular acceleration is this limit as delta t goes to 0. Now, angular acceleration, So to help you get a grip on this, we're going to really look at this one carefully because this one's the simplest possible case. So let's look at a counterclockwise rotation that is speeding up. All right, so we're looking from above. We're looking at something that's rotating counterclockwise. So the angular displacement is going to be positive, like we talked about. It's positive for counterclockwise rotation. And the angular velocity is increasing. It's speeding up. So it's starting out slow. It's getting faster and faster and faster. So it's speeding up. It's kind of like one of those tires you see on when they fix a tire in a shop. Fix a hole in a tire. They place your tire on this machine, and they can spin it around. Well, to balance a tire, spin it on this machine. So if it's starting from rest, and it's rotating counterclockwise, and it's speeding up, that's the situation we're talking about here. It's speeding up. So in thinking about how the acceleration works, the acceleration is going to be in the same direction as the velocity. The angular acceleration, it's how the angular velocity changes, is in the same direction as the angular velocity. That means it's going to speed up. The same thing that happened with a car on a road. You're stopped at a stoplight, you push on the accelerator, your velocity is in that direction, your acceleration is in the same direction. That means you're going to speed up. That's this case here. So the other cases, let's look at a counterclockwise rotation that's slowing down. So in that one, I've got a counterclockwise rotation. It's going fast. So this would be like the wheel balancing machine that's slowing down, or your tires when you step on the brakes. They're rotating less and less fast. So it's going fast, it's going slower and slower. So it's really, the angular velocity is in this counterclockwise direction, but it's slowing down, not speeding up. So that means that the angular acceleration is in the clockwise direction, in the direction opposite the angular velocity. And that's a negative angular acceleration. Then the other two cases are listed here. So let's do an example and see if we can start to get an idea here. The angular velocity of the fan blades of an engine changes from negative 110 radians per second to a negative 330 radians per second in 14 seconds. So let's look first at these numbers and see if we understand what they're saying. This is angular velocity. The initial angular velocity is negative 110 radians per second. Okay? And the final angular velocity, we just normally call it omega. And by the way, this is the Greek letter omega. I didn't mention that yet. This is not a W. A lot of students call it W. Please don't be one of them. Get used to saying omega. You can sound cool and impress your friends. It's a Greek letter omega. It doesn't look like this, like a W. It has kind of a curly Q to it. That's a Greek letter omega. The final, so this is the initial, and the final is negative 330 radians per second. So what does this minus sign say? I might ask you, what does the minus sign say? And you say, well, doesn't it mean that the rotation is clockwise? And I say, yeah, this is a clockwise rotation. Both these are clockwise. So the angular displacements and the angular velocities are both clockwise. Okay. Now, the final is bigger in, it's rotating fast finally than it is initially. So it's it's accelerating, it's speeding up. So now this is the case where you have, so imagine that instead of rotating counterclockwise, well, let me do it on the board here, I think you can see it a little bit better. Instead of being counterclockwise, I'm rotating clockwise, and I'm speeding up. What can we say about the average acceleration? We're going clockwise, we're getting faster and faster and faster, and so we're actually accelerating in the direction of the angular velocity. So we would expect the angular acceleration to have the same sign as the angular velocity because it's accelerating. This sign means we're rotating counterclockwise. This sign means that we're accelerating in the same direction. So it's this case here, C, that we didn't actually talk about. It's negative. The angular acceleration is negative for clockwise rotations, that's certainly true, that are speeding up. So in fact, instead of writing this, I'm just going to put this here. That's where this minus sign comes from. It's negative because we had a clockwise rotation that's speeding up. All right. We've just justified why we're going to get that negative sign. Let's actually figure out the math. The average angular acceleration is, remember, it's the change in angular velocity divided by the change in the time. The change in angular velocity is the final minus the initial. So what we're going to want is omega minus omega naught over delta t. And here's the final, omega, negative 330 radians per second. We're subtracting the initial, which is negative 110 radians per second. So we get negative 330 minus a minus 110. Well, that's just adding 110 because minus a minus is a positive. And we get negative 330 plus 110, which gives me negative 220 radians per second. Then we're going to divide by 14 seconds, and we get this angular acceleration. All right, another example. A jet engine has angular acceleration of negative 2.5 radians per second squared. Which one of the following statements is correct concerning this situation? Assume that counterclockwise is positive as always. So the angular acceleration is negative 2.5. It's negative. So let's go back to those four statements and see which could apply here. Either of these two could apply to this situation because in both B and in C, the angular acceleration is negative. Okay, so two ways to get it is this case here, it's negative for clockwise rotations that are speeding up. We could get it that way. Or we could get it for a counterclockwise rotation that's slowing down. So clockwise is speeding up, or counterclockwise is slowing down. Let's see which of these statements will fit. The direction of the angular acceleration is counterclockwise. Yeah. Let's look at some of these other ones and come back to that one. That one's a little bit trickily worded. What about this one? The direction of the angular velocity must be clockwise. Well, these guys here refer to the angular velocity, omega. It could be either clockwise or counterclockwise in this case. So in this case it is, this is case B, and this is case C. In case B, that's right, it's clockwise, but we could also have a counterclockwise rotation, and so that would violate B. The angular, and this is B and C from that list of talking about this B and this C, not to be confused with the B's and C's listed over here. All right, let's look at C here. The angular velocity must be decreasing as time passes. Well, we found that it could either be speeding up or slowing down, so it's not necessarily true. If the angular velocity is clockwise, then its magnitude must increase as time passes. Well, angular velocity is clockwise, then its magnitude must increase as time passes. And that's exactly this case. So here's our answer. That one, if we're clockwise and we're speeding up, then that satisfies it. E, if the angular velocity is counterclockwise, then its magnitude must increase as time passes. Well, here's an angular velocity that's counterclockwise, and it's actually slowing down. So that won't work either. And it doesn't actually, this is a little bit misleading way of thinking about it. So really our answer is D here.